So let's start today with Bohr's atomic model. In the last, what did we do? We did the quantum theory, Planck's quantum theory, in which we did that lambda that is equal to h upon mc. Okay? So today we will start the Bohr's atomic model. As we had already studied that in the Rutherford's atomic model, it could not explain the spectrum of hydrogen, and it could not also explain the stability of the atom, right? Now when these two flaws were seen in the Rutherford's model, the next model was given by Bohr, which was known as the Bohr's atomic model, and to overcome all those flaws which we saw in the Rutherford's model, Bohr gave his model. So let's go on to the postulates of Bohr's atomic theory. Right? What were the main features of this theory? It said that the atom has a nucleus as given by Rutherford, which consisted of all the protons and the neutrons, which were together known as what? They were known as nucleons. Okay? The size of the nucleus was very, very small as compared to the size of the atom. Right? And also it is present at the center of the atom. So this all was also put forward by Rutherford. The second postulate was that the negatively charged electron it revolved around the nucleus in circular orbits. Okay? Around the nucleus in circular orbits. Now what is happening? They are negatively charged and the one which is in the center is positively charged. So this positive charge in the center, that is attracting the negative charge. Okay? So as a result, we say that force towards the nucleus it is equal to the centrifugal force. It is equal to the centrifugal force. That is the center of the nucleus or the center of the atom. It is attracting all the negative charge towards itself, and the force of the nucleus by which it is attracting, it is equal to the centrifugal force. Okay? Then the third postulate was that out of infinite number of circular paths, we are saying that this negatively charged electron that is revolving around the nucleus in circular paths. Okay? So there are infinite number of circular paths. According to Bohr, only those circular paths or orbits are permissible which have an integral value of h upon 2 pi. Okay, so only those orbits are permissible which have an angular momentum which is an integral multiple of h upon 2 pi. Right? So n over here, that is going to be an integer. It can be 1, 2, 3, 4 and so on. Right? So if we are talking of the first orbit which is known as the K shell. Okay? So according to Bohr, if this is the nucleus, these are the circular orbits, then this is shell K, this is shell M, L, M, N and so on. When the shell is K, then the value of N that is going to be equal to 1. So for the first orbit, the angular momentum that is going to be h upon 2 pi. Right? Then when we travel, when the electron is in L, then the value of n that is going to be equal to 2, and the angular momentum mvr that is equal to 2 upon 2 h pi. So it cannot be fractional. It has to be an integral multiple of h upon 2 pi. In a similar manner, if we are taking the third orbit L, for L, n is going to be equal to 3. Therefore, NVR will now become equal to 3 by 2 h upon pi. Okay, so this is how he said that only those orbits they are going to be permissible who have a value of angular momentum as an integral multiple of h upon 2 pi. ठीक है? It cannot be 1.5 h upon 2 pi or 2.5 h upon 2 pi. It has to be a integral multiple. Okay? So this was the third one. Then the fourth one was, now as we can see over here that the values they are integral multiples. So therefore the orbits they were also known as stationary orbits. All the permitted orbits they were known as stationary orbits, or we say that the angular momentum is quantized. It has a fixed value for each orbit. Okay? Then after that, alright. Then the fourth postulate of Bohr's atomic theory was that when an electron is staying in one particular orbit, right? If we say that the electron that is staying in K, it will have the same energy. The energy does not change till an electron shifts from one level to the one energy level to the other. Okay, so it has the same energy, as a result of which we say when it is at the normal state, when the electron is at the normal state, that is known as the ground state of that particular atom. Okay, so we are saying that each stationary orbit is associated with a fixed value of energy. Is associated with a fixed value of energy, right? Now, if it is associated with a fixed value of energy, we say that when an electron shifts from one orbit to the other, for Example, the electron first is in the first orbit, n is equal to 1. Okay, then this is known as the ground state. If the electron now shifts to from 1, it is shifting to n is equal to 2. Then this is known as the excited state. Okay? As the electron moves far from the nucleus, it gains energy. As the electron moves away from the nucleus, it gains energy, which means that the energy of E1, the first orbit, is minimum, then the energy of E2, then the energy of E3, and so on, and the energy at infinity is highest. The energy of the electron at infinity is taken to be 0, where it is not having any attraction towards the nucleus. Okay, so the energies that keep on increasing when we go from E1 to E infinity, and we say that at E infinity the energy is going to be 0, where the electron has no attraction towards the nucleus. Okay, but when we are talking of transitions, transition means what? That the electron is jumping from one state to the other and then coming back. For example, electron goes from E1 to E2 and then it jumps back to 1. This is known as transition. Right? So transition means that the electron is jumping from the lower level to the higher level and then coming back. That is known as transition. So the energy of transition for E2 to E1, that is going to be maximum. And then it keeps on decreasing. And so on. Okay, so when the transition is taking place, E2 to E1, then the energy, that is the energy difference, that is going to be maximum, whereas from E4 to E3 the energy difference, that is going to be minimum. Okay? Have you understood? Okay. Now when we are talking of this, we are looking at two aspects. The first one is what? That the energy that is going from E1 to E2. The electron that is going from E1 to E2, in that case, when we are talking of, or we are saying that the electron that is going from N1 to N2, in this case, the energy will be absorbed. The energy will be absorbed, right? Whereas when we are talking of the reverse jump, that is the electron is jumping from N2 to N1. In that case, energy will be transmitted or emitted. The energy that is going to be emitted. Okay, so when it is going from ground state to excited state, the electron absorbs energy, and when it is coming back from the excited state to the ground state, in that case it is emitting energy. Okay, in both the cases what we are saying, we are talking of over here change in energy, delta E, right? So delta E, that will be equal to what? High minus E low, or you can also write it as E2 minus E1, where E2 is the final energy and E1 is the initial energy of the electron. Okay, so delta E, that is equal to this, and we also know that E is equal to h nu. Therefore delta E, that will become equal to h nu. Okay? Clear? So this is what the Bohr's theory is. Now there were many applications which were related to the Bohr's theory. Let's go on to those applications of Bohr's theory. The Bohr's atomic model, it helped us to calculate the radii of atoms. To calculate the radii of atoms. When calculations were made by Bohr, then according to Bohr, the radius of any orbit that was given by n square, h square upon 4 pi square MEK into Z. So what does everything denote over here? H is going to be the Planck's constant. Value of pi we know 3.14. M, that is mass of the electron. E is the charge on the electron. Z, that is going to be equal to the atomic number of the electron. And K over here, that is going to be what? I have forgotten. Wait, let me see. They have not given, that is why I have forgotten. K is a constant. Okay, so let's see again what is R over here. That is going to be equal to n square h square upon 4 pi square m e square kz, right? Where n is equal to the orbit in which the electron is present, the principal shell. H, that is going to be equal to the Planck's constant. M is the mass of the electron, E is the charge of the electron, K is a constant, and Z, that is the atomic number. Now over here, basically all these values, that is when we are talking of H, we are talking of pi, we are talking of M, or we are talking of E, we are talking of K, all these they are a constant. By putting the values of all this, it was seen that the value of R, that was coming to as (0.0529) n square upon z nanometers, okay, or 52.9 n square upon z picometers. So when the value of the first orbit of hydrogen was calculated, so it came to R of hydrogen, that is equal to 52.9 into 1 square upon 1, right? So it was 52.9 picometers. Clear? And if we wanted to calculate radius of the second orbit, then what is going to be the radius of the second orbit for hydrogen? That is going to be equal to 52.9 into n square, because z is always going to be equal to 1. For the second orbit it will be 52.9 into 4. 2 ka square, which is equal to 4. Okay, so this comes to what? 211.6. Okay, please but remember the units, because you can see over here, otherwise you will have some flaw in the decimal points. So this is going to be 211.6 picometers. If you have to calculate in nanometers, that is 0.0529. If you have to calculate in Armstrong, then it is 0.529. Okay? So this was the first application. Then the second application, calculate the energy associated with electron in the energy level. So when he calculated in a similar manner, he put that energy that is equal to what? When we are talking of energy, that is the sum total of kinetic energy and potential energy. Okay? If it is a sum total of kinetic energy and potential energy, by putting the values of both, the value of energy that was given by minus 2 pi square k square me raised to power 4 upon n square into h square. Again over here also the value of pi, k, m, e and h, they all are constants. Okay? So by putting the value of these, energy was calculated in different units. In the first unit, the value of energy was 2.18 into 10 raised to power minus 18 upon n square. Okay? In order to also take the atomic number into consideration, into z square, and the unit for this was joules per atom. So when we are doing the questions regarding the energies, please be sure to see the unit in which the answer is given to you. So the value of this has to be taken, because this is a constant value. The value of this will have to be taken according to the unit which is given to you in the answer. Okay, so if it is given in joule per atom, then 2.18 into 10 raised to power minus 18 upon n square into z square has to be taken. Then if it is taken in electron volt, then it is 13.6 into z square upon n square electron volt per atom. And if we have to calculate in kilojoules, then it is 1312 upon n square into z square kilojoules per mole. Okay? So this is the values of energy which you have to see. So energy in the nth shell can be taken as all the three values. You have to be very particular about the units in this question. And certain values which you can even, remember is that if you can make a table out of this, that when we are talking of the En that is going to be this. If you are talking of the energy of the first orbit of hydrogen atom, that is going to be minus 2.18 into 10 raised to power minus 18, because N is coming as 1, Z is also coming as 1. Okay. If you are talking of the second orbit, then it is minus 2.18 into 10 raised to power minus 18 divided by 4. Right? 2 ka square. And if you are talking of the third orbit, then it is minus 2.18 into 10 raised to power minus 18 divided by 9. But if you are talking of hydrogen-like atoms, what do we understand by hydrogen-like atoms? Hydrogen-like atoms means that they should have only one electron. Okay, for example, He positive. Now He has 2 electrons. He positive will have only one electron. So it is hydrogen-like atom. In a similar manner, lithium 2 positive. Lithium positive is, lithium has 3 electrons. So lithium 2 positive will have only one electron. In this case, you have to specify the value of Z also. Right? So if you are taking it for helium, it would be 2.18 into 10 raised to power minus 18 divided by n square, the first orbit, into Z square. The atomic number of helium is 2. So over here it will come as 4. Okay? Square of 2, that comes as 4. Have you understood? So this is how the energy that was calculated for each of the, you can say, energy levels by Bohr's theory. Then third application was to calculate the velocity of the electron. Talking of the velocity of the electron, we already know that the angular momentum of the electron, that is given as what? mvr, that is equal to nh upon 2 pi. Okay? So mv can we have to calculate the velocity. So velocity in this case, that will become equal to nh upon mr into 1 upon 2 pi. Okay, so basically when this is calculated over here, we get another formula for velocity, that is velocity into nh upon 2 pi, that is equal to ze square. Where z is the atomic mass and e, that is equal to charge of the electron. Okay, or velocity can be given as h is constant over here, 2 pi is constant over here, and e square is also constant over here. So the value of velocity that is given as 2.188 into 10 raised to power 8 upon n centimeter per second. This is the value of velocity which can be taken. So if you are taking velocity of electron in the first shell, v1, that will be equal to what? 2.188 2.188 into 10 raised to power 8 centimeters per second. So it is almost traveling with the velocity of light. The velocity of light is 3 into 10 raised to power 8 meters, sorry, that is meters per second. This is centimeters per second. So it is slower or faster than light? It is slower than light. Okay. Similarly, when you have to calculate V2, so V2 that will become equal to what? 2.188 into 10 raised to power 8 upon n. N over here that is going to be equal to 2. So this comes to 1.094 into 10 raised to power 8 centimeters per second. Okay, so this is how you can calculate the velocity. Right? So when we are talking of velocity, we are taking the ratio of V1 upon V2 over here. Value of V1 that is equal to 2.188 into 10 raised to power 8. ठीक है? Upon value of this is 2.188 into 10 raised to power 8 into 2. So the ratio of V1 upon V2 that is equal to 2 upon 1, or the velocity of electron in the first orbit that is twice the velocity of the electron in the second orbit. ठीक है? And you can calculate the ratio between V1 and V3 also. So if we are calculating between V1 and V3, then V1 that will become equal to what? 3 times V2. Okay, then we also calculate the time period of revolution. Time period of revolution. When we are talking of time period of revolution, in this case the time period that is given by of the n revolutions 2 pi r upon Vn, the velocity in the nth level. Okay, it is given by 2 pi r upon Vn. Vn we know how to calculate. The value of Vn that is going to be 2.188 into 10 raised to power 8 upon n. Right? So you can put the value of velocity over there and calculate the time period of revolution of electron in the nth orbit. Got it? Now, the most important application of Bohr's atomic theory was that he explained to us the hydrogen spectrum. Okay, and the question now came was that although hydrogen has only one electron, still it is giving us various lines in the spectrum. Like we did many series, we did 6 series. The first one was Lyman, Balmer, Bastian, Brackett, Fund and Humphrey. So we had done 6 series. The question was how come that one electron was able to produce so many lines when we are looking at the spectrum of hydrogen. So let's understand that, the interpretation of hydrogen spectrum. Interpretation of hydrogen spectrum. Now let's say, according to the Bohr's atomic theory, you can see over there in the figure, what are we saying? That there is one electron, the nucleus in the center, and then we have the K shell, we have the L shell, we have the M shell, and we have the N shell. Right? When we are looking at the first series, that is the Lyman series. For Lyman series, we said that N1 that is equal to 1, right? And N2 that is equal to 2, 3, 4, 5 and so on. running straight from fifth to first. There are many lines which can be observed. It can travel, suppose these are the, let's say these are the 5 orbits which I am showing by lines, which is also shown in the figure over there. For this n is equal to 1, for this n is equal to 2, n is equal to 3, and let's say n is equal to 4. Now if the electron is over here, the electron may jump to the third level only. It may jump to the second level, or it may jump to the first level. Right? So what are we saying over here? That the transitions when we are taking, these are the kind of transitions which can happen. Right? Or in other words, we can say that the electron is jumping from the fourth to the first. For line and series, when we are talking of only, it is jumping from third to the first, and it is jumping from second to the first. In a similar manner, when we are looking at the Bohr series, for Bohr series, n1 is equal to 2 and n2 that is equal to 3, 4, 5 and so on. Okay? So again, when we are drawing the lines, you can see in the figure also over there. This is n1, this is n2, this is n3, this is n4, and let's take another one. So we are starting from here. n1 is equal to 1, n2 is equal to, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and n is equal to 5. Now when we are talking of Bohr series, in case of Bohr series, the transition has to take from the second level, because n1 that is equal to 2 over here. So the transition can take from fifth to second, the transition can take from fourth to second, and from third to second. Again we see various number of lines. So this helped to calculate the number of lines in the spectrum. The Bohr's model has the maximum number of formulae from which the questions can be given. So all these formulae, they are very, very important when we are talking of NET or J-mains. Okay, structure of atom you can get 2, and even sometimes in NET you can get 3 questions. So all are formula and conceptual based. So when we are talking of number of lines, the number of lines that is given by n2 minus n1, n2 minus n1 plus 1 divided by 2. This is how you will calculate the number of lines. Okay, let's say that there is a transition which is taking place from n1 is equal to 2 and n2 that is equal to say 4. So number of spectral lines you are expected to calculate over here, they are going to be 4 minus 1 into 4 minus 1 plus 1. Okay, so 4 minus 1 that is equal to, divided by 2 also. So 4 minus 1 that is equal to 3. This and this gets cancelled into 4 divided by 2. So the number of spectral lines which are going to come over here, that is going to be 6. Clear? And if we are saying that the transition is taking from n1 is equal to 2 and n2 is equal to 5. So the number of spectral lines will now become 5 minus 2 and 5 minus 2 plus 1 divided by 2. Okay? 5 minus 2 is 3. So over here it will be 5 minus 2, that is 3. 3 plus 1 is 4 into 4 divided by. Okay? So this is how you can calculate the number of spectral lines. Now according to the Rydberg equation, we saw that 1 upon lambda that is equal to nu bar is equal to 109677 1 upon n1 n1 square minus 1 upon n2 square into z square. This was the Rydberg equation. This formula or this expression also gave us the fact why there was different lines seen in the emission spectrum or the absorption spectrum. Okay, that was because when the electron was jumping to different levels, the value of lambda was also given differently. Okay, because the value of lambda was different, therefore there were various lines which were seen in the spectrum. Okay, so when we are talking of this, we know that lambda E according to Planck, that is equal to h nu, or that is equal to hc upon lambda. So over here h is a constant and c is also a constant. Therefore delta E, that is inversely proportional to lambda, which suggested that if delta E is inversely proportional to lambda, therefore delta E should be directly proportional to wave number, because 1 upon lambda, that is equal to wave number. If we are getting higher value of wavelengths, then the energy associated with the electron, that is going to be less. And this explained the trend of transition which we had done, that if the electron is going from E2 to E1, that is going to be highest, because lambda is going to be lowest over here. Okay? And then after that the transition from E3 to E2 and so on. So this is our Rydberg equation that was explained on the basis of Bohr. Have you understood? Okay. Then the last topic over here, that is ionization energy. When we are talking of ionization energy, we know that ionization energy is the amount of energy required to remove an electron from any isolated gaseous atom. So when we are talking of ionization energy, we say that ionization energy, that is equal to energy of the electron at infinity minus energy of the electron in ground level. Let's say we want to find out the ionization energy of the electron when it is in N1 state. And when it is in N1 state, let's calculate in electron volts per atom. It is equal to minus 13.6 upon N square into Z square. When this is for N1, that becomes equal to minus 13.6. Okay? So ionization energy will be equal to E infinity, that is equal to 0. We have already said minus 13.6. So ionization energy has the same value as that of the energy of an electron in any shell, but this is positive and the other one, that is going to be negative. Okay? Have you understood? This is the difference. Now when we are talking of ionization energy in the first level and we are talking of ionization energy in the second level, so I1 upon I2, that can be given as Z1 square upon N1 square minus, into N2 square upon Z2 square. This is again a very important formula. Okay, so from this, if the ionization energy of 1 is given to you, for example, they are saying we calculate the ionization energy of say lithium in the second level. So you can calculate by this formula. Is it clear? So this is again an important formula. In spite of so many drawbacks, the first drawback was it could not explain the spectrum of multi-electron systems. multi-electron systems, which means it could only explain the spectrum of those systems which had one electron, hydrogen and hydrogen-like ions. Okay? Number two, although it explained the hydrogen spectrum, there were very fine lines in hydrogen spectrum about which he did not give any explanation. So finer details of hydrogen spectrum could not be explained. Also, he could not explain the Zeeman effect. Right? What was the Zeeman effect? That is the effect of magnetic field. Magnetic field on hydrogen spectrum. On hydrogen spectrum. Okay? And he could not explain the Stark effect. Stark effect is the effect of electric field. Effect of electric field. Right? So this was the Bohr's model. In the next lecture we are going to do questions on this. Okay?